Good afternoon, everybody, and welcome to episode number 10 in our series we call Trench Talk. And the goal of Trench Talk is really to share some insights into design and service related to geothermal. So today's subject, I call it Manifold Design, but it's more than the manifold. And we'll get into those details. But before we get started, I want to thank Source Rock Geothermal for sponsoring this episode. And for those of you who don't know Source Rock, they're a company dedicated to providing turnkey geothermal loop installations in New York State. Many of our contractor customers who do geothermal have historically done their own loop installations or scrambled to try to find a driller to make a vertical loop installation. Well, Source Rock takes care of all those details and allows our HVAC contractors to focus on doing HVAC work, and they can outsource this turnkey service. So if you haven't reached out to Mike Wiley, I would encourage you to do so. A manifold. It's a very simple device. Its function is to distribute a fluid to multiple parallel circuits, or conversely, to collect fluid from multiple parallel circuits. It's a simple device. And frankly, what's so hard about designing a pipe with multiple taps on it? Well, frankly, it's not very difficult. The manifold itself is pretty straightforward. However, the secret to manifold design is all about the flow requirements of the circuits. That's both the required flow in gallons per minute, and equally as important is pressure drop, because pumping energy, I've seen so many jobs where pumping energy is enormous. I go back some 25 years and I did an energy audit in Pennsylvania on a geothermal system. It cost more to operate the circulating pump than it did all the heat pumps combined. And that just points to a lack of attention to pressure drop throughout the system, but also importantly is the loop field. So we're going to stress that as we go forward today. The considerations when looking at a loop field design. First and foremost, you have to remember the sole purpose of the loop field is to transfer heat. Temperature is the main driver, not flow rate. And I wish I had a nickel for every engineered geothermal loop field I saw that engineers felt compelled to put a balance valve on circuits. And it's one of my pet peeves, and that's what has driven me to talk about this subject today. Because keep in mind that all the circuits are going to receive the same temperature fluid, because it's all coming out of the building, whatever the heat pump did to it, whether heated it up in the summer or lowered the temperature in the winter. Every circuit in your loop field is going to receive that same temperature fluid. So if there's flow rate discrepancies or imbalance between one circuit and another, it'll simply result in a slightly different temperature change going through the loop field. So if we're sending it out to the loop field at 25 degrees on the coldest winter day, one circuit may come back at 30.2 degrees and another circuit may come back at 29.8 degrees, just due to the different flow rates. But that difference in temperature, or delta T, is not important. Turbulent flow is important. And we use a line in the sand called Reynolds number of 2,500, sort of a dimensionless number that indicates the turbulence or lack of turbulence in a flow. And if you're not turbulent, you're laminar, and laminar flow presents much more resistance to heat transfer than turbulent flow. But the interesting thing is the transition from laminar to turbulent flow occurs somewhere between a Reynolds number of 2,000 and 4,000. And I don't know the history of why geothermal has drawn a line at 2,500, but what makes it go up to 4,000 is long, straight pipes with a smooth interior surface. And that's exactly what we have in geothermal. So I'm not sure 2,500 is a magic number. I would encourage you to look more at numbers above that. But once you go above 4,000, you're pretty much guaranteed you got turbulent flow. And anything higher than that really doesn't buy you a whole lot. Turbulence is also important at peak load conditions. I've got many questions over the years about when we vary the flow through the loop field, and there's times when the flow rate is much lower than our peak flow rate, and therefore our Reynolds number is going to go down and we're going to have laminar flow. But since we're not at peak load, we're not concerned about it. We're getting enough heat transfer to handle part load. So all our analysis calculations should be done under peak flow or peak load conditions. Once you're turbulent, increasing flow rate has little effect on heat transfer. Having a minimum flow to create turbulence is more important than balanced flow. Excessive flow means higher pressure drop and more pumping energy, not necessarily more heat transfer. And finally, balance valves, if you look at the specifications, are typically only accurate to plus or minus 5% at best, and impose a minimum pressure drop of at least 2 psi or 4.6 feet of head in a wide open position. But that's based on a certain flow rate. And if your valve is at all undersized, even in a wide open position, you can get much higher pressure drops. So balance valves not only give you the upfront cost, but penalize you with extra operating cost. So keep that in mind as one of your considerations when designing a loop field. Speaking of pressure drop, here's an equation. It's a very theoretical equation based on fundamental energy calculations, the Darcy-Weisbach formula, and it's got all sorts of interesting stuff in there, a friction coefficient, the length of the pipe, the velocity of the fluid, the hydraulic diameter in feet, the density of the fluid in slugs per cubic feet. When's the last time you had to deal with a slug? And I don't mean one of your coworkers. Another formula, Hazen Williams. It's a much more commonly used formula, but it too is full of interesting numbers and exponents that you aren't normally used to dealing with. But I'm here to tell you there is a much simpler method. And I say this because I see too many jobs done without pressure drop calculations really being done. And it's a tedious task, but when you simplify these formulas, it makes it an easy task. And there's really no excuse for not rigorously calculating pressure drop. And this simpler method, you can calculate a new pressure drop whenever you have a reference flow rate and a corresponding pressure drop. You can then calculate the pressure drop associated with a different flow rate. In this case, the pressure drop of a new condition is equal to the pressure drop that you have as a reference times the new flow rate divided by your reference flow rate squared. And the way to remember this is if you double your flow rate, so the new flow rate is twice as big as your reference flow rate, that's a ratio of 2 squared is 4. So you always put the new flow rate on top of this ratio and you square it. So if you double your flow rate, the squared goes to a factor of 4. So your new pressure drop is 4 times larger than your reference pressure drop. Using reference data. So the key to being able to do this quickly is to have a set of reference data. So if we create a table with nominal pipe sizes on the left and your DR, or your diameter ratio, because we do use a variety of DR pipes in geothermal, typically from a DR9 to 15.5, but we put in here 7.4 all the way up to 17. And you fill out this table with reference flow rates. So these numbers, these flow rates correspond to a velocity of 2 feet per second. So you can also consider these reference flow rates as a minimum purging flow rate for that given nominal pipe diameter and DR. For example, an 1.25" pipe, DR11, you're at a flow rate of 9.1 GPM, and that correlates to 2 feet per second. So we've got all these reference flow rates in a table. And what we want to do is characterize the reference pressure drop at those flow rates. So this table illustrates the feet of head per 100 feet of pipe. So now that you've got both of these numbers, you can very easily calculate pressure drops at different flow rates. For example, our 1.25" DR11, our reference flow rate is 9.1. The reference pressure drop is 1.3182 feet of head per 100 feet of pipe. So we start with that ratio of 12 divided by 9.1. The ratio is 1.319. We square it to get a factor of 1.739. We multiply that times our reference pressure drop, and bingo, our new pressure drop is now 2.292 feet of head per 100 feet. Now, I typically like to carry 4 significant digits through the calculation process, knowing full well it's not that accurate, but it gets rid of round off errors and gives you a little better number at the end. But I would only have faith in 2 significant digits at the end of the calculation. And to adjust for a different length of pipe, let's say we got 800 feet of 1.25" pipe. Well, you take that ratio of 800 divided by the 100 that everything's based on, you get a factor of 8, and you multiply our new pressure drop of 2.29 times 8. So 800 feet of 1.25" pipe at 12 GPM will have a pressure drop of 18.3 feet of head. Now, this seems perhaps a little rigorous if you're doing it all manually. But before we get into doing more calculations, I want to illustrate this with an example. This is a project we did at the University of Albany, and it was a very large project. We had 15 circuits off our manifold, and the loop field consisted of mostly vertical bores. But we had an area which jumped out at us as a very unique opportunity. And it's this horizontal rectangular area in the loop field. And over in the lower right here, the civil engineers incorporated an underground stormwater dissipation system. So they buried these strange looking igloos underground and dumped all their stormwater runoff into these igloos. And there was a lot of them, but I don't know the exact number, but probably at least 15 to 20 of these igloos side by side. And we suggested that we bury a horizontal loop field underneath it, because all this stormwater is going to trickle down through the formation, bringing thermal energy, or the ability to get rid of thermal energy, and enhance the heat transfer of our horizontal loop field. So it was a rather unique opportunity, and I encourage everybody designing geothermal to look for opportunities that may be a little different, but as long as you can absorb heat or get rid of heat, I would take a serious look at it. So, using a calculator, you can do all these calculations quite easily. And I'll bring over my active worksheet and sort of walk you through it. And this is the example at the University of Albany. We had different number of loops on circuits. Circuit number 1 had 13, next one 14, 15, and all the way down to 10 on circuits 13 and 14. And our horizontal field had 18 1-inch loops for a length of 590 feet. Now, we also use DR11 pipe in all our loops. So you have to enter all this data, your design flow rate, and we were targeting 10 GPM per vertical loop. Now, we really had no idea what the right flow rate was through our horizontal field. We seated the pants, figured out that it might be equivalent to about 10 vertical loops, but it all depended on, when it rained or when the storm water was active and when it wasn't active. So we just put roughly 100 GPM, and 99 was our design number. So we characterized each of the circuits of the manifold here, and then it calculates the GPM per loop. It looks up our reference flow rate and our reference pressure drop based on diameter and DR. So these numbers are all calculated or looked up. And then we have supply and return pipe. What is the length of the pipe to get out to the middle of the reverse return manifold? What diameter pipe did we use? What DR was that supply and return pipe? And you'll see here, our horizontal field, we went with a 4-inch supply and return. The groups that were closer to the building, we went ahead and reduced the diameter because we did want to impose a little higher pressure drop on that supply and return pipe to enhance the balance without going to the trouble of putting a balance valve in. We simply dialed it in using pipe diameters. And it's a trick we've used quite often on other projects where you can literally mix and match. You can put a certain length of 4-inch and then another length of 6-inch to dial it in as precisely as you want. And then we calculate the supply and return by looking up a reference flow rate and a reference pressure drop for that diameter and DR of the supply and return pipe. We calculate the loop delta P or pressure drop. We calculate the supply and return pipe pressure drop, and we add them up to calculate the pressure drop of each of our circuits at the design flow rate. Now there's a serious flaw here as far as, because all these circuits are in parallel with each other and the supply manifold is at one pressure and the return manifold is going to be at a different pressure, the pressure drops of every circuit has to be equal. So this gives us a starting point, but what we have to do is adjust the flow, recalculate a flow rate that would make every circuit have an equal pressure drop. And the way we do that, we look at the average pressure drop of all these calculated pressure drops. And now we're going to calculate a flow rate based on achieving that 9.1 feet of head pressure drop. And it's sort of the reverse of the other, that simple formula. We solve for flow rate based on a known pressure drop of 9.1. So we calculate the actual flow rates we can expect in each one of these groups. And then we look at it compared to our design flow rate. So it doesn't change much. Our horizontal loop came in at 80% of our design. But, and if I had a vertical loop that was also at 80%, I might look at making some changes. But because the horizontal loop is going to be intermittent, we didn't worry about it. Those that were closer to our manifold, yeah, their flow rates are going to be slightly higher. But still, with the degree of differences between these groups, our flow rate differences are generally less than 5% from design. And a balance valve can't improve that. So live with 5, 8, even 10% difference, because as I said earlier, flow rate isn't that critical. So then we calculate, okay, what is our GPM per loop? And it's pretty close to our design flow rate. And then we calculate the Reynolds number. And all of them are definitely turbulent. So we're in good shape. However, this is based on 18% propylene glycol. If you wanted to take it to 23% to get down to a 15-degree freeze point, bingo, our horizontal loop now becomes laminar and it jumps out at you. If we get lucky and maybe it's a cooling dominated application, we don't have to worry about antifreeze, we could put pure water in there. And you can see how much better pure water is from a Reynolds number standpoint. But you can pick your antifreeze. That's what we started with, 20% propylene glycol. And the antifreeze you select also increases the pressure drop. So what we calculated with water only now goes up by this antifreeze factor. And then we want to say, okay, our loop field is going to be roughly 10.8 feet of head pressure drop when we have 18% propylene glycol. So I think we did okay by having a fairly low pressure drop in such an enormous system. So with that, we're going to jump back to our presentation. And I'm going to give you guys a bonus for showing up today. If you want a copy of our spreadsheet, I ask you to put your email in the chat box indicating you'd like a copy. I don't normally hand out my spreadsheets because I'm not in the business of doing software support. So you can get a copy, but it's yours at your own risk, and you might find it useful. So I'd be glad to share this simple spreadsheet. So with that, I pretty much conclude my remarks for the day, but I do want to hear from you guys. And in the chat window, feel free to enter any questions. And also, Charlie, my assistant, is posting a evaluation poll, and I'd encourage you to give us some feedback. It's a simple poll, and click on this. So it looks like I'll probably let you all out early today, but I hope the subject matter was meaningful to you. And the only way we're going to improve our content is with your feedback. So I greatly appreciate that.
We do have a question.
Wonderful.
Do you count for T's, elbows, and other fittings in the ground loop? That's from Steve.
Well, you do by converting it to equivalent length. So instead of actual linear feet of pipe, you do want to add a certain footage in for elbows, T's, fittings, and generally there's not a lot of fittings in the ground loop supply and return. So you don't have to bump the actual footage very much. 5% will probably get you real close, or you can go to the trouble of adding up all the elbows. And frankly, you shouldn't put a lot of elbows in a loop distribution system. But indeed, you want to use equivalent lengths, which is actual length plus the fittings in their appropriate extra equivalent footage. So good question. Okay. Any other questions? I see my buddy Hydro Heat Pete out there. Come on, Pete. I'm looking for a question from you. I do see a question. What is your design temperature for the fluid in the loop? Certainly in our neck of the woods, Northeast, I have no problem pushing heating design temperatures down to 30 and cooling design temperatures. I design at 85 because cooling's a little less forgiving than heating. By that, I mean, if you've underestimated your cooling load and the loop goes up to 90 or even 95, I don't worry about it. These heat pumps will certainly operate at those higher temperatures. So I typically design between 30 and 85. Most large projects like the University of Albany and Skidmore College and a bunch of others we've designed, they turn out to be cooling dominated. At Skidmore College, we've done numerous projects there, and they're still operating on water only. So, which is a huge benefit if you can avoid antifreeze, but it's a little risky because where it's going to freeze is inside the heat pump, and you may end up popping a heat exchanger when it freezes. If you lose flow inside a heat pump, a zone valve fails to open, which you should always incorporate safeties, either a flow switch or an end switch on a zone valve or a two-way valve. But if you freeze solid pure water in a heat exchanger, it could very easily fail. And then you could get moisture in the refrigerant system. So I cautiously say, if you can get away with water only, great, but keep in mind, it is a risk. But the cost of antifreeze on these large systems is exorbitant, especially today with oil prices back up. Propylene glycol is directly related to the price of oil. We generally don't see methanol used on commercial projects, so propylene glycol is more common. Residential projects, I think methanol is a great antifreeze. I just don't want to be in the business of selling it and storing it in my shop. So we provide propylene glycol as a matter of convenience. Not to ask for the pressure drop counts. Okay. I hope everybody else is seeing my screen. I see Charles is not seeing the screen. Well, I also see a note that from Charlie reminding everybody that our trench talks are available at our library on our website. So if you didn't see the screen throughout this, hopefully you can see it in the recording. All right. I don't see any more questions. I'm going to let you all go home early today. So hopefully we'll see you back here in a month and we'll talk about another subject. So thank you very much, everybody. Have a great evening.